Good evening, everyone. We have with us Professor Siddhartha Gadgil for the talk Formal Proof Systems and Artificial Intelligence. Professor Gadgil did B.Stat from Indian Statistical Institute. He completed his PhD from California Institute of Technology in 1999. He was a Simons instructor at Stony Brook University. He joined ISI as an associate professor in 2002. He's currently a professor at Indian Institute of Science in the Department of Mathematics. I now invite him to begin with his talk.
Oh, thank you very much. Yeah. So, thanks Shiva and the organizers for this invitation. It's a great pleasure to be here and speaking. And first time I'm speaking at ICTS, so I've been here many, many times. Okay, so I'll be talking about an intersection in some sense of three things: mathematical reasoning, formal proof systems, and artificial intelligence. And so there is a growing sense among many people independently that these three working in combination have great potential. I mean, first, there is evidence on that. Though a lot of the potential is in the future, so much of the talk will be one part or the other of these rather than they overlap. Okay. And of course, artificial intelligence, everyone hears of all the time these days, and there are too many loose statements, both over and underestimating it. So I'll kind of follow two ground rules when I talk about artificial intelligence. One is to be empirical, go on what is actually observed. And the second is to focus on tasks and capabilities, not on whether an AI system is really this or really that, but whether it can do this or can do that. Okay, and what it would take to try to make it do this or that. That is the most useful way, assuming that we want to understand things and also whether we want to use them. Okay, so generative AI, of course, has become a popular sensation. Everyone knows ChatGPT. Okay, in particular, large language models can generate code, database queries, etc. What is less well known, but is getting increasingly known in mathematics, is there's been a big growth in what are called formal proof systems or formal methods or interactive theorem provers and so on, both within mathematics and in industry. So this is kind of recognized because one of the plenary talks in the latest International Congress of Mathematicians was about this, and there are more and more workshops and so, but still nowhere near ChatGPT. And these two complement each other very well. It's pretty obvious why they complement each other as you see them. May not be obvious yet to you because most of you would probably not have seen formal proof systems, but that's what I want to try to make clear. So there's a great potential in the interaction between mathematical reasoning, formal proof systems, and artificial intelligence. Okay, so to begin with this talk, so as I said, I want to be empirically grounded, so it will be very example-centric, and I'll give glimpses of various things. I'm going to start with examples of mathematical proofs, and these are very elementary proofs. I want them because we want common examples to talk about. I want to make some comments about proofs. So rather than general ones, let's start with something from school. Sum of angles of a triangle is 180 degrees. Here's the proof you'll find in Wikipedia. Consider a triangle ABC and draw a line through, so if you have the triangle ABC, draw a line through A parallel to BC. Now you can use the equality of opposite interior angles. The red angle is red angle, blue angle is blue angle. And use the fact that the angles on a line add up to 180 degrees. So we use some properties of parallel lines. We used pretty much by definition, the total angle is 180 degrees. But crucially, we also used an auxiliary construction. This is what I'll comment about. We drew that line from there. Okay. Here's another famous proof. There are infinitely many primes. This is the Euclid. There are infinitely many, well, there are finitely many, but a very large finitely many proofs of this. But I will talk about a very old one. Okay. For any n, we show there is a prime p which is bigger than n. This will show there are infinitely many primes. And the main idea is we'll consider the number n factorial plus 1. You all know where n factorial is. And pick its smallest prime factor. Now, if p is less than or equal to n, it must divide n factorial. So it cannot divide n factorial plus 1. So it's a prime bigger than n. Okay, so this is a proof that there are infinitely many primes. So these two proofs are given as examples because we want to understand mathematical reasoning. both human and computer in general. So there are two crucial components for reasoning. They are not just mathematical. Daniel Kahneman, who passed away recently, actually, Nobel laureate, talks about system 1 and system 2 of thinking. This view is widespread. It's well known in many fields, including at neurological levels, that you have an intuitive system. And what your intuitive system helps you do is find analogies, associations, etc. So in particular, when you make an auxiliary construction, you draw a line through A. There is no particular reason why you drew that. Okay, something told you that from based on familiarity and trial and error, etc. You could have drawn a circle around the triangle. You could have drawn a incircle. You could have drawn some other, I don't know, join it to the midpoint. You have many choices. So the fact that you did that comes from analogy, okay, auxiliary constructions, also which theorems to use, which definitions to use. And in more sophisticated proofs, proof has many steps. And along the way, there'll be some lemmas that you will prove. Which one should you prove? What lemmas should you prove? Okay. These are things that come out of our intuitive thinking and within mathematical reasoning. And then there is the logical or algorithmic part. This is following rules exactly. There are deductions and computations. So your problem solving, there's partly following rules, partly you don't know what to do, but you have seen similar things. You have associations, analogies, which we do this. Now, intuition in general is based on tacit knowledge, which is defined as knowledge which is hard to communicate. Most basic example of tacit knowledge is riding a bicycle. You can help a kid learn to ride a bicycle, but you're not explaining instructions on moving handlebars and pedals, swimming. Okay, lots of things are based on tacit knowledge. This is knowledge which you cannot, which is acquired by learning. A speculative comment there is that perhaps the reason you have to acquire it by learning is an actual description is very long, what is technically called high Kolmogorov complexity. So you can't describe it fully and tell it to another person. Each person has to acquire it. Interestingly, you can copy weights from computers to computers, so you can transmit learning to some extent. Okay, but to do mathematics, not solving problems, but actual mathematical discovery, you need another component, which is modularity or abstraction. This is not another way of thinking, this is rather another task. Okay, so let me sort of say a few things in general about this. So what is modularity? This is not specific to mathematics. Its history is very interesting. There's a very nice book by Simon Winchester called Exactly, where he describes how it came about with design of rifles. So each rifle used to be different from every other rifle. And then some French gun makers realized that if you make the components standard, there are three basic components of a rifle, the lock, stock, and barrel. So it leads to the English phrase. If one rifle's lock jams and another rifle's stock jams, you can interchange and you have at least one working rifle. Of course, this is taken to an extreme in the modern world. If I look at this computer and clicking this, it makes some change at molecular level with the electrons. And no human can understand all the steps from this to that. What you have, I didn't say what this is. So I started with the example. So let me say what modularity means. So modularity means being able to decompose it into parts. It's not a big deal. I can decompose anything into parts. Okay, typically in a hierarchical way. Our bodies are like that. We have our bodies and we have organs, tissues, and engineered products are like that, down to chips, transistors, etc. Okay, and the crucial point is the surface or interface through which a component interacts with others is simple compared to the complexity of the component itself. So this is how you can manage a very high degree of complexity in the world. The fact that you're built up of components, and components do interact with each other, but the interactions are much simpler than the details of the component. So each person at the next stage, when you're working with a chip, the chip comes with a specification of how it behaves. You ignore what makes the chip work and just deal with the specification of how it behaves, all the way up to operating systems and many layers of softwares. So details of the components are abstracted. That's what we use abstraction in mathematics. In software engineering, the people do these things very explicitly. So knowledge is also very modular when you're studying, let's say, the brain. I mean, you're trying to study how some part of the brain is working. You know, it all comes down to potassium-calcium balance between cells and hence electrical things going on. But someone studying the brain is not thinking of potassium and calcium. They have put that aside. They are thinking of neurons transmitting from here to there. And it goes down all the way to quantum mechanics, but we can handle complexity in knowledge because of this hierarchical structure where the interactions are, internal details can be ignored and you only focus on interactions. And in mathematics, we do this systematically. And a lot of, you can say mathematics itself comes from science or the world by abstraction. But within mathematics, definitions and theorems are what are supposed to abstract things away. So once you have a theorem, you use the theorem without knowing the proof. Similarly, when you have a definition, you use the definition itself. And if a particular object is a group or whatever else you want, you just deal with it as a group and ignore the details of this. Okay? And this makes it crucial. This is crucial for dealing with complicated things. A simple example is, there's a basic theorem in number theory. It's a special case of Fermat's little theorem, which says that if you take a prime p, 2 to the p minus 2 is divisible by p. It's a completely elementary theorem. And the proof in any modern sense is that some numbers, the numbers mod p under multiplication form a group. Then you have Lagrange's theorem, which in turn is proved in terms of cosets and so on. There's a whole level of things. And I can prove it top to bottom. But if I unfold it and try to prove it without using any definitions, it will become completely unmanageable. So it will be completely ununderstandable. So I'm trying to make these points because both for working mathematics, but also for computer mathematics, going up and down levels of abstraction is a different task from problem solving. So here you're all learning problem solving. Doing mathematics involves this as well. Okay, so these were general comments. Most of the rest of the talk will be examples of things we are going to do. So the different computers proof systems I'm going to talk of, they differ in different ways. First is the level of trust you have to have. Okay, so there are people who use computer algebra systems to calculate some quantity or the other that's of interest. Then you have to trust the particular person who wrote the program you're running. And that is too much. I will not talk about those kinds of systems. Okay. The thing is, how much do you have to trust? In different systems, it is different. Okay. There is value even to low trust systems, but they are frequently wrong. So I'll not talk about those at all here. Okay. Then there are general or special systems. Do they work for just everything or just one particular area of mathematics? Most special would be a calculator. Okay. How autonomous they are, how much you have to do and how much they do on themselves. Okay, how much automation they provide to you. Are they based on purely rule-based systems or do they use intuition from learning? So do they have AI in them? And whether they can handle modularity, that will mean that internally they have to represent different levels of abstraction and they have to be able to work with different levels of abstraction. Okay. So in some sense, today's status is you can't have it all. And there are systems which have every part of it, but there is, for every piece of this, there is a system that can do it, but there is nothing that can do all of it. And perhaps in the future there will be. So that's what we want to talk about before starting. Okay. So I'll now turn to, so we'll consider various proofs. Okay, except that unverified algorithms, what we would call experimental mathematics, is the one thing I won't talk about today at all. I'm going to start in detail with one system, alpha geometry, which involves AI and which illustrates things very nicely. Part of my motivation was that I gave another talk about this, so I could reuse the slides, but it's anyway a good illustration of an interplay between these. Okay, so what is alpha geometry? The alpha, as you may guess, there'll be in various systems that are called alpha, comes from alphabet. This came out of Google research. Though interestingly, in this case, even though this is very recent, many of those people have moved to other companies. Okay, so alpha geometry, it comes from Google DeepMind, is an AI system that can solve geometry problems. So more precisely, it can't solve all geometry problems. You can state a geometry problem. If you can state it using some particular symbolic language, it can solve it. And most International Maths Olympiad geometry problems can be stated using only this symbolic representation. Not literally, it doesn't start with natural language, you have to write the problem or a picture, it starts with a problem that you can write. And very important, this is the first system that is getting close to expert human level. So if you look at how it did in the geometry problems only, so Olympiad has some 4 parts, and you compared it with the scores of humans who wrote those Olympiads, and saw how many they get. Its score was somewhere between a Olympiad, International Maths Olympiad silver medalist and an International Maths Olympiad gold medalist. Actually, it was just short of the gold medalist level. So it's far better than me, for example, at problem solving. So with these kinds. So how did it do it? So this is a very good illustration of how systems can work today. So we saw there were components of reasoning. Similarly, the components of so IMO kind of geometry problems, there's a particular symbolic language. If you can write the problem in that symbolic language, it can try to solve it. It can attempt to solve it, exactly. And that symbolic language covers most what we'll call geometry problem, elementary geometry problems. So this is a specialized system. So one of the things is I was saying you can't have it all is you have very good systems like this, but in a special area, not across mathematics yet. Okay, so what are the components for reasoning? Well, there is an efficient deduction system. Okay, so these have been developed over time. You would say all the way from the 1950s, all of computer science has been developing better and better data structures and algorithms, which will let you deduce things very efficiently. Okay, so there is, and they had some further advances in these. So given you have a powerful algorithmic deduction system, and what is called a language model like your ChatGPT, except this is a specialized one, for suggesting auxiliary constructions. I will show you examples in a moment, but we already saw an example. For example, in the first thing that I said, sum of the three angles of a triangle is 180 degrees. That extra line you drew was the auxiliary construction. There is no deductive system which will tell you draw that extra line. You could say try everything, but you will get combinatorial explosion that way. But everything else is deductive. You can look at the picture and deduce for applying theorems. Okay. So a large language model suggests auxiliary constructions. Now you need to train such a model. Okay. And to train such a model, maybe the biggest contribution of these people and what took the most computing resources was generating what is called synthetic data. I'll explain what this synthetic data is. But the analogy before starting is that there is another system called AlphaZero, which became the best chess player in the world by a very, very large margin. And the synthetic data was just playing chess against itself, starting with nothing but the rules of chess. So you're generating synthetic data. So you will run out of data for things like mathematics, but this is the way. So I'll explain what exactly is happening. First of all, what is this deductive database? So what we have to start with is a finite collection of points. And we have only points, we don't have lines because through any 2 points there's a line. So we don't explicitly say they're lines. So there we start with maybe 30 points, okay, or 7 points. And then we have relation between points and also lines through them, etc. So for example, if you see this relation perp A, B, C, D, it says A and B are distinct points, C and D are distinct points, and the line through AB is perpendicular to line through CD. So through 2 points, there's a unique line. So all relations can be written as relations between points, maybe 3 points, 4 points, or even circles. You think of 3 points determine a circle. So you have a relation given in terms of points. Everything is in terms of points. And rules of deduction, there are, there are about 13 constructions here, relations that they have. And the rules of deductions, there are 72 or something, I had counted before. They let you deduce consequences. These are theorems in geometry that you apply from these. For instance, you all know this, if AB and CD are both perpendicular to BC, then they are parallel to each other. If I take a line and I have 2 lines perpendicular to them, they are parallel to each other. This is one of the rules of deduction. And so you give it a bunch of points and you give it a bunch of relations and you can rapidly deduce the consequences. Okay. So iterating deduction with, so what you do is you start with these and keep deducing till you have stopped deducing anything new. And then that's all the consequences that you need. So the key point here is that we do not add a point. We have if we started with 8 points and a bunch of relations between them, okay, maybe we started with 8 points and you're given 7 assumptions about them. You've gone to 8 points and 700 assumptions, but you still have 8 points. Okay. So this means it's a finite process. You keep deducing things and then after a while you can't deduce anymore. This process stops. Okay. So they also added something called algebraic reasoning. They said that deduction doesn't work very well for things like ratios of lengths and sides and angles. So they use linear algebra, which I see from your worksheets you're all working in. So lots of relations can be written in the form a plus b is c plus d. They used Gaussian elimination to make this deduction more efficient. Okay. Don't want to say much about this because that's not the main point. So we have one side, we have a fixed set of points we can deduce very fast, and a few IMO problems can be solved by this pure deduction. This is building on earlier work, it's a natural continuation. What is really new in this world is how you would be able to train AI systems to do more than this. So here's how you generate synthetic data. So what you do is the following. You start with millions of random configurations. By this I mean you choose a certain number of points, 10 of them, and throw in a bunch of relations. Say I assume the points are A1 to A10, I assume A1, A2 is perpendicular to A7, A9, this is parallel to this, throw in a bunch of these random things. And then they found 100 million theorems from this by deduction. Okay. And for each of these theorems, you found the shortest proof. This was nothing new. Now, the key idea, and this is what will tell you what is non-trivial in mathematics. If somebody tells you something is a non-trivial theorem or a non-trivial application of one area of mathematics to another area of mathematics, you should have something in the conclusion which was not in the assumption, okay, or something in the proof which was not in the statement. So suppose you had a proof of suppose you started with a configuration with 10 points and you had a theorem and that theorem statement involved only 7 of them. But the proof involved 8 of these points. Then introducing the 8th point is an auxiliary construction. Okay. So in some sense you are generating random proofs and then you are observing when these proofs are not purely deductive. So you are not adding more points. You started with 10 points. But a specific theorem statement involved only 7 of them and proof involved 9 of them. So there are some auxiliary constructions involved. Okay, so then you train, ignore this, I use the slides, pre-training and fine-tuning and so on are perhaps not familiar terms. If they are familiar, you can see what this means. But broadly, the language model was trained to make the auxiliary constructions based on this data. Okay, so you don't have data ready. There are far too few human-solved problems, but you create this kind of data. Okay, and so just as a check, they checked that none of the IMO problems accidentally ended up in the training data. They were randomly generating, so randomly they could have ended up, but they didn't. So how do you solve a problem? You are given a geometry problem. Okay, you make all the deductions you can. If you solve it, excellent. If you don't solve it, then you ask your GPT like language model to suggest an auxiliary construction. Okay, maybe it suggests 3 different ones. For each of them, you make all the deductions. And if one of them works, you're done. Okay, if none of them works, then you make more auxiliary constructions and do a tree search based on these. Okay, so for some or all you do it, then you do what is technically called a beam search. Okay. So this is a little details about one system. I think things will become clearer with this picture. This is a picture from the alpha geometry paper. Okay. So you can see there are 2 example problems. One of them is a simple problem, but still needs non-trivial. Take a isosceles triangle, that is AB is AC. Then you want to prove that the angle ABC is angle BC. Well, from AB is AC, actually there's nothing you can deduce directly. The rules of deduction tell you nothing. What you have to do is make a construction, which is take the midpoint of BC, as you see. So it was not solved, nothing was in fact deduced. You take the midpoint of BC and drop, call that D and add the line AD. And as soon as you add this, you can deduce that ABD and ACD are congruent triangles, from which you deduced AC is BC. Okay. So you tried to deduce, you got nothing. Then you ask this oracle-like language model, what shall I do now? Construct it. It told you suggest this construction. Okay. And you would do this. Now this you could probably brute force, you try lots of simple constructions and one of them will be this, but this doesn't scale. The second one is another very complicated picture. This is an IMO 2015 problem. By the way, if you hear people talking about computers solving IMO problems, it's important to note that they've got harder over the years. So some people you'll see lots of hype things. We solved 2 IMO problems. You'll find that IMO 1962, which was a lot easier than these days. Okay, so IMO 2015, and you can see from the proof, it was quite a non-trivial problem. It involved 3 different auxiliary constructions, which are highlighted here. Okay, I don't even know the problem. I would certainly never be able to solve a problem like this, not even close. But the alpha geometry was able to solve it, and it involved lots of deductions, but also the deductions would get stuck and trying various auxiliary constructions and doing a search. Okay, so there are a bunch of other examples which I'm going to skip in the interest of time and not having to rush. So the point I wanted to make about this is today we are already reached the stage where the 2 components of, so the lessons from this alpha geometry is that you can combine intuitive methods with deductive methods, and you have computer-based systems that can do both. And you don't necessarily need a lot of data to train systems. You can make synthetic data by playing around and trying it some. Maybe this is why kids play, because you're generating synthetic data about the world. I mean, in some sense, that's true. As we explore or we play, we are just sort of learning more and more about the world. Okay, so there are very nice things for symbolic integration and fun search and so on. As I said, I'll skip up, which are all these AI systems. Okay, so these were the things. The other point is that, I mean, the auxiliary constructions, many of them, the suggestions would be useless. So you need to have 2 sides to this. You need to have an intuitive system, and you need to have a deductive system which complement each other to work this way. Yeah. Sorry. This particular system works only for geometry proofs, not just only to proofs. That's a good point. Yes, for this particular system. I mean, many things people are working on will also approach open-ended problems. For example, I don't think I had saved written examples, but I've asked GPT for open-ended problems and then asked them to prove it. And yeah, so there are issues there. Yeah. So this particular system, you have to tell it the conclusion in advance. But that's actually a thing where there is a bit of a controversy within the certain aspects of this community, because sometimes the IMO problems are open-ended and they are translated to the problem where you are given the answer. And people say that makes it significantly easier. But then people in AI solve the easier problem and say they solved the original one. Yeah. So this is an issue that it is easier if the answer is given rather than open-ended one. But this particular system doesn't make that false claim. It truly sticks to only proofs, and there are other things that go beyond. Yeah. Okay, so I'm going to give a sort of quick high-level view of deep learning and language models. And because statistics is one of your themes here, it's actually very useful, because I almost, when I was going to first speak here, was going to have my title as is machine learning statistics, which is a story in itself, not because I want to debate, but simply because the comparison helps one understand things. So let's start with what is deep learning. Okay, so in deep learning, we use data to learn a function of a specific form. Okay, so people have seen linear regression here, right? Or in this? Huh? Just started, but they know the concept of y equals a. Huh? Okay, you may or may not know. You'll soon see linear regression. So what is traditionally done in statistics is that you have a bunch of points, and the very old style is you fit a line to it. You try to represent it as a linear function. So deep learning starts off by saying, why stick to linear functions? We'll use a different class of functions, which is a composition of functions. Okay, each of which is just a linear function. Ax is just a matrix A times x. Add a constant and apply some specific sigma, what is called a sigmoid or something, one specific sigma. So these are not complicated. The sigma is fixed, only the matrix entries and the vectors B, what is called bias, have to be learned. So you're fitting this class of functions. And chain rule of calculus gives you a method which is called backward propagation, which lets you fit these functions very well. Okay, so you gradient flow towards it. Now you do many versions better than gradient flowing, but the chain rule lets you fix these functions differently. Okay, that linear transformation may not be an arbitrary matrix. It may be a special form like convolutions and so on, but you can ignore that. So Broadly, this is just like statistics, except you're using a much larger class of functions. Because you're using a much larger class of functions, you can fit many more things. But the catch is that you need much more powerful computers. So the deep learning revolution happened around 2010, and the ideas come from the 1980s. All the ideas for the start of the deep revolution. The only thing that progressed between 1980s and 2010 is hardware. You had faster computers and specifically graphic processing units, which more or less following the same ideas, you could fit far larger functions. So far things are parallel. But then things started taking off, and they took off with this paper called Word2Vec, which I'll mention, representation learning. This is just over 10 years ago. In fact, some months ago, they had the 10th anniversary of the conference where it was published, and it got an award for a test of time paper. I think more fields should have these things, saying that 10 years later, you see which papers presented 10 years ago have proved really important. Okay, so what we do is you learn functions as a composition of C composed with phi. Okay, where phi is you think of as capturing meaning and C is giving you the actual answer. So just like humans, when you're trying to answer a question, you think of it as two parts. You understand and capture meaning, and then you actually calculate or whatever to have the answer. But what does this think of mean? So the idea is that when you want to learn phi, which is the meaning of it, you take an entirely different task and solve that task instead of the original one, which will help you solve the problem. Okay, this was abstract, but let me give a concrete example, the first concrete example in a sense, Word2Vec. Okay, so what it did, Word2Vec, what that did is that you looked at a huge amount of text. There's lots of text in the world, of course. And given, let's say, any set of 5 words, you know the 4 on the ends, you try to predict the middle word. Nobody actually wants to predict the middle word. But the way you predict this middle word is you think of this prediction as a composition of 2 things. You map the words into a space, and then you use a standard algorithm which, given points in a space, use that to predict the word. And then you forget the algorithm and remember only the mapping. So what you have done is you have captured, effectively what this does is it translates meaning of words into geometry. Okay, so this is what is called representation learning. You learn to represent the world in a good way as points in a vector space, so that words get mapped not to how they're written, but to their meaning. So you capture things this way. This opens the way, once you start thinking this way, for the next step, which is transfer learning. So suppose you have a bunch of tasks, all with the same input. And an actual example in production here, Google switched its translation somewhere around 2018 or something to this. So when they were handling close to 100 languages, initially for each pair of language, they would train translation separately. But now if you're trying 100 pairs, it's ridiculously large, and you're not going to get data for that. So instead you say that if you want to translate from English to any other language, these are all related tasks. So your task is you're given a bunch of English text and you're told the language you want to translate to is Kannada or Swahili or whatever else you want. And it's a single task. Okay. So what you do is you use common layers. So you think of the first step as being common for all the tasks and the rest of it being separate for all the tasks. Okay. So, and it was found that if you have a network trained for one task, the specific training for another task goes down a lot. That's because in some sense training for one task, it's understood the world a bit better. Okay, yeah, so I already mentioned this translation. So next step would be to group the tasks as one task. Okay, so and you would have translation to different languages. So with this, you have sort of moved away from the usual, at least basic statistics to the extent I know it, where you're solving a particular problem with a particular piece of data. Instead, what you're trying to do is you're training to understand the world, and you're doing it by playing around, in a sense, by solving problems that nobody cares about the answer to. But you're solving those problems only because they help you understand the world. And then finally, you do a little bit of training for your specific problem. And you can think of GPTs as the extreme case of this, where everything has become one task. Predict what comes next. Answer the question. That is only one task. Okay, so you can think about this. This is a way. One thing that came is there was one more technical issue that went into GPTs. This is a paper with a very nice title. It's Attention is All You Need. Okay, so there is something called a transformer architecture. I won't go into any technicalities, not that I know them very much. Okay, so it's based on something called attention. And the relevant point is this allowed massive parallelization. So the technical advantage of transformers was simply that you could train parallelly on an enormous scale. And with that you could train models. And when you start increasing scale, you don't know in advance, are things going to keep getting better and better, or are they going to plateau? So as you get bigger, it'll get better, but is it going to go like this or like this? And well, we know the reality, they just kept getting better. We haven't yet reached the limit of scaling, and we have reached quite high levels. Okay, so here's a little bit of a summary. So this was a digression into looking at large language models. I want to talk about their interaction with what they have. So they have remarkable abilities roughly corresponding to our intuition. Okay, they can reason by analogy. This is a crucial point, and including mixing and matching concepts from different points. So you can see this visually. If you haven't seen, you can go and search. You'll see pictures of was it a polar bear? Polar bears swimming butterfly in the Olympics, and you can generate this. Now there is no direct analogy. What it has done is it has put many pieces together. So it not only can analogically reason, but put pieces together. Oops. Sorry. I pressed a button that I didn't know existed here. Okay. And they're excellent at natural language. This is what has suddenly given them access to all our literature. So they can learn from what we write for other humans to consume. They're familiar with a huge amount of stuff, and they can also combine broad knowledge with specific knowledge from their input. However, I won't go in examples at detail. I have many. I've experimented very heavily, thanks to Microsoft giving me credit. They give utter rubbish a certain fraction of the time, and they're terrible at avoiding logical fallacies and judging correctness. Okay, so the most extreme version of this I've seen. This is from GPT-4, not 4.0 or 4 Turbo, but the original GPT-4, which a few months ago was the strongest model. You had a proof by contradiction. It said that if this was true, so-and-so number must be 4, but it is 4, hence contradiction. Okay, so 4 is not 4 was a literal contradiction. So when I say it's terrible at judging logical fallacies. Okay, so, I wasn't supposed to go to more. Sorry, I have to. This was a section to skip. I'm skipping. Okay. So now I'll move to different kinds of systems, more deductive systems. So we looked at deep learnings. So one of these are SMT solvers, or SAT solvers. Let me skip details of this. These solve finite problems. Okay. This is the original P or NP problem. I'll give you just an example of a problem that they solve. This is a problem asked by Ron Graham in the 1980s, Boolean Pythagorean triples. It's an intriguing question. So you know there are Pythagorean triples like 3, 4, 5, with 3 squared plus 4 squared is 5 squared, and 12, 13, 15 I think is one more, and so on. Can you color the integers with 2 colors, say black and red or something like that, so that whenever I have a Pythagorean triple like 2, 3, 5, not all 3 can be black and not all 3 can be red. So they can't be monochromatic. Can you color all integers with this Boolean? So it was an open problem until 2018 or so. And the answer is no. And you can do it with numbers up to something like 7,500, and then you can't do it beyond that. This was proved by what's called a SAT solver. So these are powerful methods that things that can solve many other sort of open conjectures have been solved. These are purely deductive, powerful methods. Now these are limited to finite problems, but there's a larger class, resolution theorem provers with unification. They can solve problems in first order logic, which includes in principle all of mathematics. But in practice, as I said, it doesn't handle abstraction or modularity, so it must handle only a few axioms. The most famous case, this is a little less general, what's called a term rewriting system, was Robin's conjecture. This was conjectured in the 1930s. Until 1996, it was an open problem, and many leading logicians worked on it. For example, Tarski set many of his students to work at it. Tarski is one of the top people in logic of all times. So it was a characterization of Boolean algebra is the structure of true and false. You can, true and false, you have or, and, not, and certain properties. So this was a conjecture that said this one equation gives you a Boolean algebra. Okay, if any of you see baby group theory, you'll see similar kinds of statements. And it was solved by a system called, it was conjectured in 1830s, it was proved in 96 by automated theorem prover. So these are examples of deductive problems. They're impressive, but they work only on a small scale. So in practice, first order logic is not suitable even for representing a lot of mathematics. What you use are interactive theorem provers. So there are software systems where proofs are obtained by human machine collaboration. And the computer checks the correctness of the proof and also helps you find it. Okay? This allows formalization on a large scale. So you have a digitized mathematics on a large scale. In particular, Lean Mathematical Library has most undergraduate mathematics and quite a few, growing numbers of advanced topics. Nowadays, more and more recently proved results as well. Yeah. Yes, so my next slide is addressing that. So you enter the proof in a particular language and the computer will tell you whether it is correct or not. Correct. This was the question. Who guards the guards, right? Is that your question? How do you trust the computer? If the computer told you it is correct, how do you trust the computer? Yeah, so who guards the guards is a saying from, I don't know, Cicero or something from antiquity. It's saying, it's like, I guess negative, infamous case in Karnataka where the Central Vigilance Commissioner deputy, someone in the anti-corruption office turned out to be corrupt. And so this is the question, who guards the guards? This was a very crucial point. So I always have this slide when I talk about it. It was addressed in the very first system by De Bruijn, and it's called the De Bruijn principle. Okay, so this is the point. How a computer verified proof is only as trustworthy as the system that verifies the proof. So De Bruijn, when he designed automath, followed the following principle. So following the De Bruijn principles, the computers are verified by a small trusted kernel. Okay, a small amount of code. Okay, which you can thoroughly check. In the modern world, it is open sourced. If you want to trust the proof, you go and check the kernel. Okay, the analogy which came up in a conversation with somebody is you think of these interactive theorem provers as chess playing programs. One part of it, which is the kernel, is just checking legal moves. Now you can imagine that checking legal moves is enormously easier than figuring out what move to make. So you separate out that part and you check that that program is correct. So no magic can happen. There'll be another issue that will come up in a moment. So you can check up. And in particular with the Lean theorem prover, which actually Leo de Moura, the creator of these, takes these issues very seriously. It has a bunch of independent type checkers. So not only do you have Lean's own kernel, which is small, there are two others. One is called Lean for Lean, both written in Lean, and Lean checker, but they are both written in Lean 4. And since Leo was not happy with this, they commissioned someone to write in Rust, an entirely different language, something which checks Lean's proofs. So before Lean's proofs are accepted in the library now, you have 4 independent pieces of code checking it, and one of which is in an entirely different language. These type checkers are non-trivial because one task that I started was actually porting the Scala checker and I have not completed. So yeah. So this is so how do we trust it? It's because this De Bruijn's principle. Finally, it has to come to humans understanding something and trusting something. So this is like I said with modularity. You cannot do magic and get things correct. What you can do is a small surface. You can say there is this little surface. If there is an error, the error must be here. Please take a microscope and check that particular surface. That's the thing. There are other possibilities. Yeah. No, Lean itself. So Lean theorem prover is also a programming language, a very pleasant and fast programming language. So there is Lean's own compiler, which is written in Lean, and there are 2 other programs written in Lean themselves. So when it came to Lean 3, there were actually 4 independent type checkers. One in Lean, one in C++, so Lean 3 was written in C++, one in Haskell, one in Scala, and one in Rust. Lean 4, the others haven't been ported yet, so yeah. So, but there is another failure point. What if you actually prove, somebody told you you proved, claimed they proved Fermat's last theorem or proved the Riemann hypothesis, but actually they proved 2 plus 2 is 4. So you could still have wrong definitions, and you could have wrong statements. This has to be human checked. There is no avoiding this fact. But, so as I said, you cannot get magic, but it's orders of magnitude easier to check that definitions are correct. And there are other known facts used, which when I did formalization with this undergrad Anand, we did it too, and they did it in a famous project I'm going to mention, which is you want to check your definitions, you prove a few extra theorems with those definitions. And the fact that you could prove those theorems suggests that your definition is correct. You gather evidence, that's all. Yeah. So a couple of famous instances of this kind of thing. This what was called a liquid tensor experiment. Peter Scholze, who is a Fields medalist, in December 2020, he challenged the formalization community to computer verify a foundational theorem of condensed mathematics. So Scholze and Clausen are creating an entirely new way of doing a large amount of mathematics called condensed mathematics. And there was a very central theorem. And as he said, with this theorem, the hope that condensed formalism can be fruitfully applied stands or falls. So it better be correct. This is a foundational theorem. He has a lot more to say in the blog that announced it, as well as the blog where the answer came, some of which is quite amusing. It's worth reading. So one of the things he said is that for many months he was very worried there may be a small mistake. So he kept asking many groups, have you checked this? Many people were running seminars on this, and he found that everybody had stopped short of checking details of that theorem. And one of the comments he made is he said he knows he is very good at convincing people of proofs, even if he's wrong. For example, he got full credit in the German Maths Olympiad for wrong solutions that he had given. So he said one of the reasons he's worried is he has a track record of being convincing even when he's wrong. So he wants to be correct. And the lean community took up this challenge. Johan Komela led this. And I should also mention Adam Topaz, who subsequently became a very major leader. Many people contributed. Scholze didn't write any lean code, but collaborated throughout these, fixing mistakes found along the way. In about 6 months, a major step was solved. And Scholze said at this point he was satisfied. This is the part he was worried about. But anyway, in a year and a half, it was fully solved. So this was set. Now, Scholze said that he actually understood his own proof better after this lean work. A more recent example, this is called the polynomial Freeman-Ruska conjecture. So Gowers, Green, Manners, and Terry Tao proved a long-standing conjecture. It was called the polynomial Freeman-Ruska conjecture. Okay, when you have two Fields medalists in a proof, you know it's important anyway. So what Terry Tao did is he started a problem to formalize this in lean. Terry Tao is a very remarkable person. He knew that this was coming. So before that, he said he has to learn lean. So he, with community's help, formalized something himself so that he knew what he was talking about. But when this paper was announced, just a couple of months before that, he announced this to the world. And it was a relatively self-contained piece of mathematics. With the liquid tensor experiment, a lot of background work had to be done. Here, there was no background work. And indeed, it was formalized in about 3 weeks. So that was there. About 20 people contributed. So the point about these interactive theorem provers, so I've jumped from AI to interactive theorem provers. They'll come together again for a little bit. So proof in lean is not only correct, but it's modular with precise abstraction boundaries that are fully respected. I will give examples to clarify this. As I said, a theorem is supposed to be an abstraction boundary. You only use the statement of the theorem. However, it is common enough in mathematics to say that so the theorem says there exists such and such. We see that the proof of the theorem actually made the construction which has some additional property. So that is a leak. If you want to use that additional property, it should be part of the statement of a theorem. All this causes mess. And then of course there are assumptions that are missed in the statement, etc. Things are not correct, and so the second point is each piece is correct exactly as stated. This makes things easier for the reader, Okay, so it allows you to focus on different levels of details of the proof. There is this extremely nice tool under development by Patrick Masson and Kyle Miller and so on, where you have a kind of textbook and a student can unfold to the level they want. If they understand this proof, fine. If they don't understand one piece, more details, and in principle all the way down to logical proof. Okay, and the biggest gain, so while correctness is very important in software, realistically mathematics gives a guarantee of correctness, but nobody died because the theorem was wrong. So that's not what causes people to have pushed for ITPs so much as the collaboration is facilitated. Because normally collaborators, you have to trust the person who contributes part of a proof. And also, it is difficult to contribute to a proof if you only have expertise in one subject. That's because everything is always slightly wrong. And so you apparently solve a proof, but it will not exactly fit. But since things are exactly correct and exactly sealed, you can have people with only one piece of expertise. This allows, Terry Towers said this, for example, you had 20 collaborators in the formalization of the polynomial Freeman-Russa. So much larger scale collaborations from much more diverse people and even with partial expertise. And the greatest benefit perhaps of this is that the collaborators could include GPT and other large language models. As I said, they are very powerful but very unreliable. So you could have them suggest it, and if their suggestion is wrong, throw it away, and if their suggestion is correct, accept it. Okay, so yeah, slightly slower than I planned, but that's fine. So let me just, now we bridge. So I talked about ITPs, I've mentioned. So let me talk about a task. Auto-formalization. So this is something in between, is automatically generating lean code from natural language. This is useful even if it's sometimes wrong, because you can filter out what are wrong, or a human can correct them, etc. So a very interesting paper called Draft, Sketch and Proof, about an year ago, did the following. They used a large language model to generate proofs. These proofs were translated to proof sketches in some formal language. Why? Miss saying that, actually a language called Isabelle. And then you used algorithmic automation to complete the proofs. So the idea was and they found that this method did very well on high school level problems. Okay, so you draft, you sketch, and then you prove it. Now you could try to refine this, and it's well known this works with program with iterative feedback. That is, you say this step is wrong and ask the language model to correct it, etc. And what I'm working on and many others here and there is related to this. Okay, so demo. This is my code running. This work with collaborators, of course. So here is lean, and somebody doesn't know lean. Well, I pretend I don't know lean, and I write in English, please state the theorem. There are infinitely many odd numbers. Okay, rather a silly theorem. Now you see, it worked, and then it offered me the translation into lean. Okay, so this is an auto-formalization tool powered by GPT-4. So this is one of the ways in which you can have the two things here. So this is of course not anything great by the modern standards, but the advantage of talking about things that I've done is it will illustrate how you work with large language models. Okay, so we are given the statement of a theorem. What do we do? If you simply ask it translate to lean, it won't do it correctly. If you say write it in Python, it might, because it's seen a lot more Python code. But you ask it to do it in lean, it won't. What you do is you find 20 documentation string in the leans. Lean has a huge mathematical library with similar statements and their translation, and give it to these as examples. Okay, and then you give it the prompt and ask it for 10 responses. And then you discard responses that are invalid lean code. And this suddenly gives vastly better things. So general view with large language models is you go and type and ask ChatGPT. It's okay. It can be quite impressive at times. But when you want precise answers, give it examples, give it data, and then post-process what it comes through checks. We also do one more kind of post-processing, but it has a very marginal effect in this example, majority voting. We group together equivalent statements and go with the largest group here. It has a very marginal effect, so I'm not doing it. So here are just pictures of the example. If a vector space is two-dimensional, then it is finite dimensional. That was one of the examples I gave. Okay, so we give it the prompt, and it translates it to lean. So this was one of the 40 test silly statements. Okay, so there is always the issue of contamination. GPT-4 has seen this in its training before. And so hence it was able to solve this problem. This is always a concern. So we had two ways of defending against this. And one way, so we did give a bunch of 40 theorems. One way was this, which is what I did, which is I made up silly statements. You can be assured that no textbook has a statement that if the vector space is two-dimensional, then it's finite dimensional. Yes, obviously silly statement. So GPT-4 did not see the answer. It managed to translate to this. So we had 40 theorems. The theorems had some contamination, and also 40 false statements. Again, we are sure that there aren't false statements proved in the literature. Maybe we shouldn't be so sure, but these were simple enough that we could be sure of these. Interestingly, sometimes GPT-4 asked for a translation, said this statement is false. And sometimes it did something else subtle. We made false statements by tweaking the hypothesis, it corrected them as well. Okay, but excluding the ones where it outright said it's false, you had an 85% success rate. So things were working quite well. Okay, so I have only 5 more minutes. Let me give you a few examples of GPT-4 in action and then conclude. Okay, so here I asked GPT-4o, which is now available to everyone in case you did not know. So till about 3-4 weeks ago, what you got on GPT was GPT 3.5, and 3.5 is much worse than 4. I know I've used both of them extensively, but from recently we all have access to 4o, as it is called, which is better than 4. And so I asked it infinitely many primes ending in 7. So Kevin Buzzard, mathematician, who has done a lot of this lean formalization, in a talk took this as an example of ChatGPT being silly, because you ask it prove there are infinitely many primes, it gave the proof. And you ask it prove there are infinitely many primes ending in 7, it gave the same proof with just ending in 7 thrown in, and of course that proof was rubbish. But if you ask ChatGPT today, it says that you have to use Dirichlet's theorem on arithmetic progressions and gives you this proof ending in 7. It finds the arithmetic progression, it checks GCD, etc., etc. Okay. So to save time, I have many more examples, but we won't linger on this. So this is showing that it can do quite non-trivial things. GPT-4 correctly answered many non-trivial questions, including one we asked our PhD students, and my colleague insisted this is not a very standard questions. Okay. In particular, he pointed out that anybody who answered that we selected for our PhD program, so GPT-4 would be selected, except that it answered some simpler questions. It gave garbage, it gave wrong proofs. And it repeatedly used false statements in proofs. For example, it assumed that if a sequence is increasing, it's unbounded. That was part of its proof, quite persistently. Now you ask it, is it true whether every increasing sequence is unbounded? It says no, it gives a counterexample. So it's not even internally consistent. So the logic here, I mean my general view after a lot of experimentation with GPT-4o is the correct way to think of dealing with these systems is you do not think of them as stupid or smart or whatever, intelligent. They can be stupid at times. What they are the ultimate smart alecks. They will never ever admit they're wrong or they don't know an answer. They're rather good. They often answer non-trivial things. But if they know something is false, they'll tell you it's false, if they can figure out it's false. But they will never admit to failure, they will bullshit instead. So they're the ultimate smart aleck. Okay, I mean, of course, we all know smart alecks are annoying, so they can be annoying, but you have to use them. So the hope is that you pair it with something like lean and with iterated feedback. And these two, and this is a hope for many people in many areas, and many people are working on these. Okay, so in addition to, one more point is in addition to, I already talked about auto-formalization. In addition to actually proving things, there are many auxiliary tasks you can ask it to do. For example, you can describe lean statements, proofs and code in natural language, and it does this. This is much easier. It does it very well. Only thing is in the prompt, I include all the definitions. So you want it to translate a statement from lean into natural language. I include all the definitions automatically and do it. It identifies mathematical terms used. It rewrites proofs in a structured format. It can examine proof and point out missing details. Okay. Wait, I went the wrong way. Okay. Sorry. Okay. So my last section. good time to conclude. So I'll turn to, let me pause before entering this section, just last 2-3 slides. So what I'm going to talk about. So as I've been trying to say, we have mathematics in the small where we are solving problems, and we have deductive systems for a long time that can solve these problems if they are purely deductive, far better than humans. And we have systems like alpha geometry which are beginning to combine intuition and these. We have interactive theorem provers which can handle but not autonomously mathematics on a large scale. And we have AI systems that can interact with them and help and automate more and more of the tasks, perhaps everything. Okay, so I'm going to make some examples. What do we actually do when we do mathematics? I mean, I don't know if I know the answer, but I've apparently done it for a while, so I'll make some sort of attempt at an answer. And like with everything else, I'm just going to focus on examples. So here is a typical mathematical thing that happens in mathematics. Diophantine equation, equation with integer coefficients. It goes back to Diophantus of Alexandria or something long ago, and many others, ancient times and many other, in India, Babylon, many other civilizations as well. You want integer solutions. So whether things have real or complex solutions is easy, but integer solutions is hard. And indeed, it was proved by Malchev, building on a whole string of works, Gödel and Turing and Church and Julia Robinson, etc., that there is no algorithm that will, given a Diophantine equation, either solve it or not solve it. However, in specific cases, in number theory, you can solve not only this, but even families of Diophantine equations, and you can also talk about the number of solutions, etc., etc. So what happens is that it's typical in mathematics that you have an unsolvable problem, or it's a finite problem, so in principle solvable, but in practice not, in generality. I mean, class of problems, but more and more in that class you can answer. Of course, famous example is x to the n is y to the n plus y to the n is z to the n. If n is 2, these are Pythagorean triples, which we saw a while ago. And if n is 3 or more, Fermat's last theorem says it can't be solved. And an enormously indirect proof of this simple thing. And that indirect one proof involves finding another Diophantine equation actually, and counting the number of that solution to get a contradiction. Here is a different example, my last but one slide. So we consider what is called a word problem. We consider words in an alphabet. With words considered equivalent if they are related by substitutions. Okay, a silly example is the alphabet has just alpha and beta, and we can substitute alpha beta as beta alpha. And again, in general, there is no algorithm that can solve the word problem. In this level, it's Novikov theorem, and there is no algorithm that can solve the word problem. Okay, in this above example, actually, you can solve it quite easily. What you can do is make substitutions so all the alphas come before all the betas. This is what is called a normal form. More interesting examples are we can show that if words of some length are related, then they're related by the number. So the reason why this problem is hard is that two words may be short, but they may take 1 billion moves to relate. So if they are related, you have half algorithms. You'll sooner or later find those 1 billion moves, but you never know when to give up. Okay, and results of a geometric nature tell you there's a time at which you can give up. Okay, so what happens in mathematics? Here's my attempt at a summary, so I've put it in quotes so that I don't get beaten up by anybody. So we start with basic questions. Maybe they came from nature, maybe they came from engineering or something like that. So we develop techniques that can answer these in some cases. General case is often unsolvable or just ridiculously hard, or you would just solve that and be done with it. And then you abstract the question and you abstract the techniques, and they become something we are studying now. So this leads to new questions. First of all, the question is whether this technique is applicable if something happens. So that's a question you start studying. And also, when you have a new class of objects, you have certain natural questions about this. And hopefully, if you progress at higher abstractions, the original question can be also answered in more cases. Okay, I gave examples. This does happen, maybe much less often than mathematicians would like you to think, but it does happen. Okay, and the hope here is that artificial intelligence and formal proof systems together will make super mathematicians which will push all these steps together. Okay, so why would we want it? We want to push these because we want to solve the original problems. Do we really want to solve Diophantine equations that badly? Maybe not, but we do want to solve other things very badly. So I end, my last slide is to talk about some biology. Okay, so a fundamental scientific problem is to predict three-dimensional structure of a protein from its sequence of amino acids. And there's a system called AlphaFold 2. A few weeks ago, AlphaFold 3 was released, which is one step further, which can do it. Now, hard experimental results, including some in Bangalore, were used to get the structure of about a few thousand proteins. And with AlphaFold 2, it's the number of proteins for which we know the structure has gone up to 200 million. It's not even comparable, the scale at which you're doing things. Okay. But for a specific protein, we don't know that alpha 2 is correct. Now, people have been using its predictions for a long time, so we know they're not rubbish, they're largely correct, but we don't know that it is correct. What you would hope is that developing mathematical theory will let us predict with proof for larger and larger classes of proteins. So, the general hope here is, in summary, large language models can be used for many core and auxiliary tasks because of their intuitive reasoning. And but due to their unreliability, it's natural to combine them with interactive theorem provers. These should hopefully give us tools for mathematics. And maybe the most optimistic view is that we can extend, the first part is not optimistic, it's happening in the real world. We can extend mathematical proofs to the cases that are otherwise too tedious and or specific. This happens in the real world. I'll just say in a couple of sentences what this is. This is a field called formal methods in computer science. There are a bunch of people working on it. For example, the Paris metro, driverless metro in Paris. You want to show no two trains are going to collide. You model the metro. It's a mathematical theorem they're not going to collide. There is no difficulty in proving this. Intel uses it to prove that chips behave correctly. It is very tedious though. There are essentially simple but millions of theorems you want to prove. No human is going to want to do this and is going to do this reliably. This is what these are used for today, but what one hopes for is that you would extend this to those kinds of problems like protein folding or modeling plasma infusion or weather prediction, which today are too hard to prove theorems in mathematics. Okay, thank you.
Thank you for the insightful talk. Are there any questions?
Yeah.
So I have two questions. Like when you talked about giving inputs to the machine, if we are trying to solve a problem, suppose A is a problem and it wants some outcome O.
Yeah.
So if the problem A is too hard for it, we'll give it some problem B which has the same output O.
Yes.
You use sci-fi as example.
Oh, okay. No, you're saying while training a machine, You're okay,
Then can we think of it as this, like suppose I am trying to make the machine learn driving,
Yeah.
where the outcome needs to be safe presence on the road. And
Yeah.
so
So
I will teach it riding a bicycle, where the outcome is also safe presence on road.
yeah, so the thing is, roughly what you said, it's not so much difficulty, but the lack of data, which is why you have different problems. Okay, so the reason why you would typically, it's not that learning an easier problem will necessarily help it with a harder problem. That it could happen to some extent, but most of the time, what the problem is the paucity of data. You can have a synthetic problem for which you have a lot of data. And so what you would do with a machine if you wanted to ride a bicycle or something is predict what a human bicyclist is going to do. I mean, before you try to get it to do this. But yes, while driving a car, you get it to be aware of things, and these days with large language models, you get it to explain what is happening, etc. So you get the reason you create synthetic tasks is because it should represent. Yeah, so you could tell it to describe every object on the road. Where tell me when you see a pedestrian, tell me when you see a divided line, tell me what are the rules applying right now, etc. before you actually start driving the car. So I think you were giving similar examples. Yes. So you do want to build it up by giving examples which are easier, but more importantly than easier, because easier problems may not help you that much in solving harder problems, problems for which there is a lot of data. And this is especially true with car and so on, driving in the physical world, because you don't want to learn. In chess, you can learn by losing a game, right? You don't want to learn by killing someone while driving a car. So it's important that you solve all sorts of problems where you can easily get data and where being wrong is harmless. Yeah.
And my second question is,
Yeah.
while introducing alpha geometry,
Yeah.
you told us that it makes auxiliary suggestions. Okay.
Yes.
So when we make some code for the alpha
Correct.
because we have done something similar before.
Yes.
So when we are introducing our auxiliary suggestion in the system, we need to feed it with some data and solve problems beforehand, right? Before giving it a synthetic data.
No, that's the thing. So the alpha geometry has two components. There is a deductive system, as I said, which is deducing, and a neural network which makes the auxiliary suggestions. And the neural network did not use any human data. It started with nothing but synthetic data. So it just created random problems, solved them, observed the ones that involved auxiliary suggestions, and used that for training. This needed very large amount of compute. I mean, this was expensive. It was literally money terms also expensive to have this. Okay, so I'll give you another example which is similar in spirit, which is older, which is AlphaGo 0 and then Alpha 0, which is a successor. So Alpha 0 is a system that learned chess. It just ran in, started knowing nothing but the rules of chess. Literally nothing else. What is a legal move and what is not a legal move. And with massive compute, just made random legal moves with itself. Played to the end, saw when it won and when it did not win. And based on this purely synthetic data, it took 2 hours to become the best chess player in the world. In 24 hours, it had rediscovered all standard openings, then discarded some of them saying they're not good, etc. And they trained it for 48 hours. By then, it had a rating way above anything anyone has seen. And if people understand chess well, which I don't, somebody has written a book about what a human can learn from Alpha 0 as well. Okay, so this geometry was the equivalent of that. Of course, that's not computationally efficient, which is that you really need to do a lot of random cases to get useful ones, because most random cases are not useful ones. As I said, they found 100 million theorems. Some million odd of them had auxiliary constructions. And that was the data it used. It did not need human data. So AI is not data limited if you can check correctness of answers. This is what is called, this is a part of it I didn't say in the summary because as it is, I was short of time. This is what's called reinforcement learning. If you have a way to score the final answer, then you do not need data to learn AI. So what you do is do it. And within mathematics also, what you can do is generate random proofs, discard those that are either trivial or wrong, and then learn from those. We also do it. I mean, every time we solve a correct non-trivial problem, we have learned something more. And next time we are solving a problem, that is part of our training. So if you have a way of evaluating, which is reliable, then you do not need data. You can generate your own data. That's synthetic data. It's called reinforcement learning. Yeah. So currently, I mean, just to add to it, in some sense, you can say there are two peaks. The famous one is things like the Everest is GPT-4o, etc., and a few of its siblings, which are large language models. And then there are things like Alpha 0, which you can say is a different peak far away, which are learned by self-play. They are more creative, they don't bullshit, but they don't work across a range of topics. You would think, why don't we combine these two? Well, in some ways, people are trying to combine these two. You can't combine by brute force, because each approach takes so much computing that you can't take the product of their compute. So you can't in a simple-minded way combine. Yeah. Okay. Yeah. Yeah.
Any other questions?
Right. Yeah, as I said, in alpha geometry as well as alpha 0, the minimum amount of data was 0. You did not provide any data, you just provided the rules of geometry or the rules of chess. No data was provided at all. You just randomly generated a configuration of points. You randomly generated a set of hypotheses, deduced all the theorems, figured out which of them were involved auxiliary constraints. For each one that you deduced, you found its minimal proof. Then you looked at which had auxiliary constructions, and that became the data for your training. So absolutely no. So in alphas, in fact, historically, when you looked at these alpha Go systems, The first AlphaGo did what is called imitation learning. It started with millions of expert games and then learned starting with that. And then AlphaGo 0 was exactly zero data. So you can do, this depended crucially on the fact that you had a reliable way of saying correct or wrong. I mean, that is the point, that, so there is this mu 0, etc. So in many things in the real world, you don't have an absolutely correct and absolutely wrong. Then it is unavoidable to have some real world data or something else. But if you have a very precise notion of correct and wrong, in principle, you can start with nothing. And in practice, in some systems, it has done it with nothing.
Okay. The session will continue outside in the foyer. Professor will be available outside. So let us thank the speaker once again.
Thanks.